So, welcome back. Here we are. We get to continue our exciting story of the models of the universe. Does it really get any bigger than that? No, it's the universe. I don't think it does. Now, last class, we talked about Johannes Kepler, and he developed his 3 laws of planetary motion. He studied those wanderers, those stars, those planets that traveled in the night sky. And he utilized the data of Tycho Brahe to come up with his 3 laws of planetary motion. So, if you would please, if you don't have it out in front of you, go grab it. Grab this handout from the packet that says Kepler's 3 laws of planetary motion. I'd like to go through that today. We'll see how long that goes. Then we're going to get into how did Newton come up with his universal law of gravity. And if that weren't enough, we'll get into how Newton's 3 laws are both the premise and the proof for the universal law of gravity being true. God, it's awesome. It's awesome. It may end up being a total of 3 videos. It may be 1. We'll see. But either way, here we go. So you guys watched, read, learned all about Johannes Kepler and his somewhat strange history. He had quite a life. But what we're going to focus on is his 3 laws of planetary motion. So in the beginning here, it says, in the early 1600s, Johannes Kepler proposed 3 laws of planetary motion. Kepler was able to summarize the carefully collected data of his mentor, rival. Are they one and the same? Tycho Brahe, with 3 statements that describe the motion of planets in a sun-centered solar system. First put forward by Nicolae Copernicus. Now, Kepler's efforts to explain the underlying reasons for such motions are no longer accepted. Nonetheless, the actual laws themselves are still considered an accurate description of motion of any planet and any satellite. So, let's take a look. First law, known as the law of ellipses, says the path of the planets about the sun is elliptical in shape, with the center of the sun being located at one focus. Let's draw a picture of that if we could. I'm going to go ahead and draw the sun at the center and a planet, let's say Earth, orbiting. Now, the sun is at the center and the Earth just kind of looks like a fried egg. The Earth orbits around in an elliptical orbit. Now, the Earth's orbit is very close to circular. It's why the ancients didn't really realize they weren't traveling in perfect circles. But it's not just that it was elliptical in shape. What Kepler did by demonstrating that the planets do not travel in perfect circles was he was able to get rid of this idea that had been around since the time of Aristotle in 150 AD. And that is that the planets travel in perfectly circular orbits. Why did they travel in perfect circular orbits, the ancients thought? Because that's a perfect form of motion and can continue on. So they thought the planets, the wanderers in the night sky, traveled in perfect circles, and Kepler showed that they did not. I think it's easier to see if we look not just at the motion of a planet, but if we were to say, look at the motion of a comet. And I know that you know from grade school on that comets have much more elliptical orbits. That's a pretty poor picture. Let me try that again. There it is. Now, interestingly enough, comets have 2 different tails. One is the dust they leave behind that's not charged, which follows along its path. And the other is the dust that came off that is charged, gets blown away from the sun by the solar wind. But that comet's orbit is much more clearly elliptical. So what is the real takeaway? The real takeaway is that the first law gets rid of the idea of perfectly circular orbits. Now, easy enough? Fair? Can we move on? I think we can. I thought that the video from the Mechanical Universe did a beautiful job explaining how Kepler actually figured out the orbit of Mars. If that didn't blow you away, There's not much else I can do for you. It's amazing. Now, Kepler's second law is called the law of equal areas. But what it really did for us to be aware of, is that it demonstrated that the path of a planet does not always have a constant velocity. So I'm going to go ahead and draw the sun at the focus of an exaggerated elliptical orbit. Maybe we'll go back to, say, the path of a comet again, like this. And as the video really nicely talked about, the velocity changes because one of the tenets, what he found, was that the area swept out during some interval of time, t, would be equal to an equal area swept out in an equal amount of time. Whoops, I'm going to make that just a little bit smaller. So I had to edit my picture just a little bit. Sorry about that. What I was saying was that the planet would trace out equal areas in equal times. What that indicates is that it is clearly moving slower when it is farther from the sun, and it would move faster the closer it is to the sun. Now, this is true of comets, but it's also true of the planets. Now, the ellipse that I drew here is pretty dramatic compared to a planet's orbit, which is mostly circular. But there it is. Now, it didn't just show that the velocity changes, although that is a big deal. What it also showed was that there was a mathematical relationship involved with the change of the velocity. Now, it turns out that it's conservation of angular momentum, which at the moment is beyond the scope of our course. But I think the real gist of it is there is a mathematical relationship. The mathematical relationship. Kepler's second law. Now, Kepler's third law, the law of harmonies, is his greatest achievement. It is. He was able to develop this 10 years after he had developed his first two laws of planetary motion, utilizing the data from Tycho Brahe. And here's what he found. He found that the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. Huh? Which at this point you're saying, what was that? Well, let's think of it in terms of a graph. Okay. What Kepler was able to do by looking at all of this data for those wanderers through the night sky was that he was able to graph, one way to think about it, different values on different axes. So if we were to graph period squared versus r cubed for the 5 known wanderers through the night sky, it turns out that they are a perfect linear line. That means that they are going to be, those two values, period squared and radius cubed, are directly proportional to each other. So there is a relationship between the period squared to the radius cubed of any of the planets is going to be constant. Now, another way we could write that would be the period of one planet to the period of another planet in its orbit squared would be equal to the radius of one planet to the radius of another cubed. There it is. There is a mathematical relationship. There's a mathematical relationship for the period and radius of a planet's orbit. Now, the big thing that I think is maybe the most important takeaway is that he derived this formula from data. And that was in 1618 when he finally published. Kepler's third law is that the period squared of a planet's orbit is related to its radius cubed. Now, I know you're thinking, what's that have to do with Newton? We'll get to that in a bit.